recording, share the screen over here, and there we go. So ready to start our big data class today. Quick reminder about Monday, there's the quiz. Any questions about what to expect for that? Okay, then today what we're going to do is we're going to finish up talking a little bit about this, the implementation details of the MVCC multi-version concurrency control, and then so that's the end of this week 10 folder. The week 11 folder is posted, and we'll start talking about this. This is, I think, basically everything in the course is building up to this material here. This week 11 material, definitely the most important part of the course. It's how we're going to start making our queries actually like super fast. And I also find it, I don't know, just intrinsically really interesting what we can do here. There's handout, the questions.pdf that has just a bunch of example questions about what to expect for the for this section of the course. And this will have both true and false sort of questions, and then more free response questions that we'll go over about when we get there. Any questions on what to expect from that? Okay. Then let's see. Yeah. So last time we'll do a quick 2 or 3 minute recap of the highlights from last time. This here is probably like, if there's one figure to make sure that you understand, it's this figure here. This is the in chapter 1 of that Internals of Postgres textbook. And again, this what's going on in this figure is that this is one of the pages in Postgres, one of the pages in the heap, and again, the heap is the name for how we're physically storing all the data in our tables. And in every page, this blue stuff at the top is our header information, which again is 24 bytes, similar to the header for the tuples, but it's a totally distinct thing. And these pages themselves are 8 kilobytes. And we store the tuples sort of growing from the bottom to the top. And every time we add a tuple, it adds just information down here going from the bottom to the top, modifying some of this header information at the top as well. And eventually we'll fill up the space inside of this tuple and have to create a new page in our heap in order to store the new information as we're inserting more and more data. This is another one of those key figures. This here is from chapter 6 in the vacuuming section. We're going to talk a little bit more about vacuuming today, but the key thing about this figure here is that when we were deleting information from these pages, we didn't actually like directly delete the information. Instead, we adjusted that X max header variable. And what that did is it made the tuple visible or invisible to certain transactions. And once there's no transaction at all that can see a tuple, we called that a dead tuple. And then that's just wasted space that's not being used at all. And the vacuum process is what goes through and recovers that wasted space. So it does it one page at a time. In this page right here, if we had these 3 tuples, this dead tuple right here, it would convert it over here, recovering that free space. But again, we said that the vacuum process, because it's only one page at a time, if we have a bunch of dead tuples like this, so here's 3 pages, the pages are entirely full, but most of the information can be recovered, or most of the space can be recovered because it's mostly dead tuples. The vacuum process by itself will just convert that, again, page by page into something like this. So now there's a lot of free space, and we could insert into these pages directly, but we didn't actually like recover space physically on the hard drive. We can now, insert without creating new pages, but we didn't actually physically recover new space. In order to physically recover new space, we need the full vacuum instead of the regular vacuum. And the full vacuum actually goes through and basically creates a whole new table from scratch and then does an insert on each of the tuples one by one, compacting things and giving us our space back. And so that's what we've covered up to last time. There we go. Make that a little bit bigger so we can see. This, so section 6.1, this outline right here has a highlight of all of the things that vacuum does. So there's many, many important things that vacuum does. The things that we just reviewed are this section right here, that it removes the dead tuples and defragments the live tuples for each page. What the defragmenting refers to is, oops, this is the picture that I wanted here. Defragmenting refers to moving this tuple 3 next to tuple 1, but it's all just like within a page still. We're not yet at the point where we can talk about removing index tuples. We'll get to the indexes here starting at today, and then we'll be able to cover this particular point here. This freezing old transaction IDs, we're not going to cover this in detail. But you will be responsible for this, so you're responsible to read this section to understand what's going on. The highlight of it is that, I'm going to come back over to our notes here to highlight the most important parts. Every transaction ID, so again, when you see the XID, or anytime you see an X, X stands for transaction, is a 4-byte unsigned integer. So that's only 4.2 billion transactions that these XIDs can store. And that may seem like a lot, but in practice, if you're somebody like Instagram, you can go through 4 billion transactions in just a day. So these XIDs aren't actually enough to store all the transactions in the history of your database. And once you've filled up these 4.2 billion transactions, then you can't do any more transactions. Postgres will lock. And this is called the transaction wraparound problem. And this freezing process right here is basically the process that gets around that. The idea is that, again, we're not going to go over this in detail, but the idea is that once you have a sufficiently large number of transactions, you're no longer using the old transaction IDs, the small numbers, and so it's a way of getting around that. And so if you're not vacuuming regularly, the main takeaway, if you're not vacuuming regularly, then you'll only be able to use 4 billion transactions, and then you'll be stuck until you vacuum again. So that's one of the important purposes of vacuuming. Today, what we're going to focus on for the vacuuming process is this section right here, updating what's called the FSM, the free space map, and the VM, the visibility map, and how those will impact the speed of vacuuming, the purpose of vacuuming, and eventually these will have a big impact on our indexes that we'll talk about. Any questions at this point before we get into that discussion? Okay, so back over here to the week 10 notes. So again, vacuum, you can call it manually by vacuum, just then the name of the table like this. But because vacuuming is so important, there's a process in Postgres called auto vacuum, which is going to automatically vacuum for you. And so the vast majority of times, especially in sort of like data analysis applications, you don't need to worry about vacuuming at all. If you're like somebody like Instagram and you really need to squeeze out performance, especially with a lot of like updates and delete sort of transactions, then tuning auto vacuum becomes super important. But for most data analysis applications, you can just use the defaults. So it turns out that vacuuming a table is an expensive procedure. And so in particular for large tables, say greater than 1 gigabyte, it can easily take multiple days to do this vacuuming procedure. And so the visibility map is a way of speeding up the vacuuming procedure. Here we go. Here's the key figure for the visibility map. This visibility map, so this green thing right here is stored as a separate file inside of that Postgres database. So here, recall that all of these numbers inside of the base directory correspond to an OID, and every relation has an OID associated with it. This OID, we have our base directory, then this first OID corresponds to the OID of the database, and the second OID corresponds to the OID of our particular relation, in this case, the table. And the _VM is the file that contains the visibility map. This visibility map is essentially just a list of bits, zeros and ones, that tell us whether a particular page has a dead tuple inside of it or not. If the visibility map contains a 0, then the page has a dead tuple inside of it. And so when we run our vacuum process, we'll have to spend time actually vacuuming this entire page right here. But if our visibility map has a 1, then this page right here will have no dead tuples in it, so our vacuum process can skip over it. And that's how vacuuming can be sped up. If our visibility map is essentially all ones with very few zeros, then vacuuming will be really fast, skipping over most of the pages, and the visibility map ensures that we only have to vacuum the pages that we actually have dead tuples inside of. The visibility map was originally introduced for this particular purpose, to make vacuums faster, but we're going to see that it's also going to make our indexes faster as well. The indexes will be using this visibility map. And so then after the vacuum process processes an individual page, it's going to update the visibility map, setting that 0 equal to a 1. Again, one of the reasons why you want to be vacuuming regularly, and so having this auto vacuum process doing that for you, is because the more you're vacuuming, the more these pages will all be cleaned, all have 1 set in the visibility map, and so the faster subsequent vacuums are going to be. Any questions about the visibility map? Okay. Yeah, so I think it's a pretty straightforward, intuitive concept. The free space map is similar, but the free space map, what it does is it tells us exactly how many bytes are in this whole area, or the free space area. Recall that the space between the end of the header and the beginning of the actual tuples is called either the free space or the whole. And the free space map is just a list of integers telling us how many bytes are in that free space. So when we go through and do an insert, we don't have to actually loop through every page, checking every page. We can just loop through the free space map, seeing which is the first page that has an opening, and insert that way. So there's no particular figure that corresponds to the free space map, but it's a similar idea to the visibility map, just storing the amount of space inside this white area, and the vacuum process also updates that for us. Any questions about either of those two things, or anything at all about vacuuming? Okay, then let's see if there's any other quick notes here. Yes. So one other difference between the vacuum and the vacuum full is the type of lock that they take. So vacuum acquires this share update exclusive lock. Again, we know that looking at the documentation over here, saying share update exclusive acquired by vacuum without full. The vacuum full command, vacuum full requires the access exclusive lock, so a much stronger lock. And if we think about like what those two commands are doing, it makes sense that the vacuum full is going to require a stronger lock because it's like totally redoing the table. So because this requires the stronger lock, the vacuum full, in practice, people almost never do a vacuum full and stick with just doing the vacuum command. Because with the vacuum command, you have the access share exclusive, the share update exclusive, and that allows you to continue doing selects, the row share, and doing inserts and updates and deletes, the row exclusive. So in practice, vacuuming is what people do and not vacuum full. The only situation I can think of where you'd want to do a vacuum full is if like you're desperately running out of disk space and need to free up disk space. But if you do that, then your database or that table is not going to be usable until that finishes. So your system, whatever it is, Instagram or whatever your web page is or your data analysis system, is going to be down for the hours or however long it takes to complete this process. Again, we're going to talk about indexes here in a little bit. The create index command is really the main one that will block against a vacuum. You can't do a create index while vacuum is running. And so sometimes people get into this situation where you really want to create an index, but you can't because the auto vacuum procedure is running. And so you have to wait until that finishes in order to create your index. And it's tempting to go through and disable auto vacuum, but that's something, again, that you never want to do. Lots and lots of bad things happen when you do that. So never disable auto vacuum. Guaranteed, this is going to be a question on the final asking about disabling auto vacuum and what the situations are that you want to do that. And your answer should be you should never disable auto vacuum. Any questions about those locks or? Okay. So one of the key things about database design that we're not really going to talk about is that depending on how you structure your tables and your code, you can actually make it possible in some situations to not use the update and delete commands and only use the insert commands for things. And that's a really popular thing to do because, again, in Postgres, when you do the update and delete, it adds that bloat to the table, making the wasting disk space and making various operations slower. So people go through a lot of work trying to prevent those operations from happening. Last thing down here, so typical, like if you have a database or a data set that's say like 1 gigabyte, can you try to guess how much disk space the database is going to use? In general, especially when you have a lot of updates and deletes, it's basically impossible to predict how much disk space the database will use. But a typical like common overhead would be between 2 to 4 times the amount of raw data that you're storing. So if you're into the terabytes of data, that can start getting like, I don't know, important, where you have to start buying more hard drives. But hard drives are cheap, $100 for a couple terabytes. So even this amount of overhead is in practice pretty negligible. Any questions about anything from the week 10 before we get into indexes? Okay. So then week 11, indexes. There's the most popular type of index is a Btree. So we'll be spending a lot of time on that. And sometimes you'll see people using these two terms interchangeably. But index is a more generic term than Btree. Btree is a particular type of index. And the whole point of indexes, what they do, they are data structures used for making our SQL queries fast. And they make lots of queries fast, but it's really the select queries that we most care about. So the upsides of indexes, so our select, update, delete statements, they would be an O of N runtime. In order to, without an index, they're O of N. And with an index, we get that down to O of log n. And one of the things that, I don't know, beginning programmers, computer scientists think is important, which is not important, is that people think that these log factors are important. So like the difference between O of 1 and O of log n is important, or O of n and O of n log n is important. And that's really just not true. That if you imagine like the biggest number that you can think of, like, I don't know, 10 to the 20, there are fewer than 10 to the 20 web pages on the internet. And if you take the log of 10 to the 20, that's only 20. So like the difference between log n and O of 1 is basically just a small constant factor. So this is really, anytime you see like log n, you can handle arbitrary amounts of data. It's basically O of 1, there's no difference. And so this reduction from O of n down to O of log n is what allows like companies like Google to search through huge data sets like the entire internet super efficiently. Another advantage, key useful thing of indexes is that they're required for the implementation of unique constraints. And we saw before that foreign key constraints require unique constraints, so also required for foreign key constraints. There are other types of constraints in Postgres, but they do not require indexes. In your that questions.pdf file, one of the things that comes up a lot is I list some type of weird constraint, and you have to tell me whether it requires an index or not requires an index. But these are really the two constraints that require indexes, and all the other ones don't require an index. Disadvantage of an index is that they add some overhead to your insert times. And because there's some overhead to insert, recall that update is implemented as a delete followed by an insert. You get a little bit of overhead in the update as well. The going down from O of n to O of log n is an update significantly like overshadows the going up from O of 1 to O of log n. And again, these two things, for all practical purposes, O of 1 and log n are equivalent to each other. The main disadvantage though, thinking about this, is that if you're adding a lot of indexes, so in some situations, you might need to add like, or you might be tempted to add thousands to millions of indexes on a particular table, that's where the inserts are gonna get really slow. But if you're just adding a small number, like, I don't know, less than 100 indexes, then there's essentially no disadvantage here at all. Other highlights. So using indexes properly basically will solve all of your SQL performance problems. The other situation where you'll run into SQL performance problems is related to vacuum in Postgres, but doing the indexes properly is going to really solve everything. And for whatever reason, my experience talking to people in industry is that most devs don't really properly learn SQL, and because of that, they have no idea what's going on inside of indexes, and so they can't make their database code fast at all. This is especially true for companies that use ORMs, so those like Python interfaces that mask SQL from the developer. Again, like Reddit is a company that does that, and Reddit's famous for being super slow because a lot of people who work at Reddit just don't really understand how indexes properly work. I'd say like if you're at a FANG sort of company, everybody there is gonna understand this sort of stuff pretty well. But if you're anywhere else, I would expect like, I don't know, maybe half of the people working there will have a vague idea of what's going on with indexes. There's a lot of comics. I'll let you look at the comics on your own time about people using, or like, I don't know, people who actually understand SQL and can create these indexes properly, make the SQL queries fast, are like just considered heroes at companies because of what they can do. Okay, so references for this section. Two important references. The first one, or I guess we'll start with the second one, this chapter 7 of the internals of Postgres. So it's the same book that we've been looking at before. but chapter 7, back in this hierarchy of things, this chapter 7 comes down here. So we've again talked about 1, 2, 5, 6. We'll be talking about 7 in this week's material. But this 7 really requires us to fully understand the indexes themselves before we get to it. And if we go again to chapter 1, at the very bottom, I mentioned this before, but there's this link to 9 different blog posts down here. This is going to be our references for how these different indexes actually work. All of these, so again, this book written by a Japanese author, all of these posts down here written by a Russian. Click on them, it takes us to this webpage, haber.com. This webpage is a Russian webpage. So all of these articles are translated from Russian, originally written in Russian. And if you're like browsing the rest of the things on this webpage, you'll see a lot of things in Russian. It's a sort of a social network for programmers to share cool programming articles. But I want to take a quick diversion based off of current events in Russia to talk about this webpage and the possibility of this webpage going down. So this webpage turns out to be hosted in Russia, and we can verify that real quick by just going to come over to our terminal over here. I want to get the IP address of the web page, so I'll do a ping of haber.com just to give me the IP address right here, 178.248.237.68. And given any IP address, you can look up where the physical location of that IP address is. So there's lots of tools on the internet to do that. Here's just one of them. And it will tell us that this website physically located in Russia. Here's the actual GPS coordinates of this website, of this server. And so there's a lot of talk about disconnecting Russia from the internet by various people right now. And so there's some possibility of this web page going down. And if that happens, there are mirrors of this web page, not in Russia, that we can link to. But I think it's important for us to look at the original source when we can. So as long as we can, we'll be looking at the original source. Some advantages of this original source is that at the bottom, if you're interested, there's like comments that people post and links to other related articles that would not be in the original source. Another quick side note is that one of my main sort of interests in computer science is how we can be using computer science and programming between different cultures to prevent wars and bridge sort of cultural gaps between cultures that are not happy with each other. And so I find it cool that even though the US and Russia are not on the best of terms right now, programmers are still working together to accomplish cool things. And I won't go into too much detail about there's lots of sort of historical examples of how that has actually impacted like on the ground political negotiations and prevented conflicts and helped diplomats. If you're curious about those things, I'd be happy to talk about that, but we won't go into that in class. So those are the references. Again, you're responsible for everything inside of those references. And we'll be talking in class, cover maybe half of the material or so, and the rest of it you'll be expected to be able to look up in the references for yourself. Any questions about the references?
Wait, so at least when you click on that first link, you only connect the first blog page. How do you get the other one?
Oh yeah, good question. So this link right here is to the first of those blog posts. The way the web pages are structured under under the haber.com website is that if you go to each one of the blog posts, then at the very bottom, there's a link to the others, all the way down to the bottom. And it just has this read on kind of hidden right here. So you can, that's one way of doing it. The easiest way though is on the internals of Postgres chapter 1 at the very bottom. It has this little information block, indexes, internals, that links to all of the things individually, sort of by topic, so you can jump around to them. This Btree one is sort of the most important one, so that's what we'll be spending the most time on. Good question. Any other questions about the references? Okay, so yeah, there's 1, 2, 3, 4, 5, 6, 7, 8 different types of these indexes of these data structures that we will be going over. And again, this Btree one, the most important one. Most of these other ones use Btrees internally. So we'll be spending a lot of time on the Btree here, especially today. That's what the rest of today will be about. And so the way this discussion is going to be structured is that there's all of these data structures, and the algorithms on the data structures, we're going to talk about them sort of separately than the data structures themselves. So we're first going to talk about the Btree. Then we're going to talk about all of the different algorithms for using these indexes. And there's again, a whole big list here in the notes with the different properties of these algorithms. And these go over, I'll talk about what they go over, but lots of different, basically every way that this data structure can be used to answer the select queries. And then after we cover like those algorithms, we'll go back to covering these other data structures and how they relate to those algorithms. But to keep our sort of discussion as generic as possible, we will be talking about, I don't know, the Btree kind of separate from the different algorithms about the Btree at first. So first thing about the Btree is that you should have a intuitive, high-level understanding of it, but you're not going to need to know like the low-level details. So when we were, let me refresh this. There we go. In your data structures class, you probably talked about a handful or at least one of these different binary search trees. In my data structures class, we do the AVL tree. But the other ones, other popular ones, red-black tree, 2-3 tree. And when you did those, you actually implemented the trees and talked about the different like insert, delete operations and how those actually work. You're not going to need to know that in this class. In this class, you'll just need to know that like the Btree is maintaining all the good properties that we want, that it stays balanced, it stays in the right order. It's always going to be correct. But you're not going to have to implement it, and you're not going to ever be asked questions about, like, given this Btree structure, if we do a particular operation, what's the result of the Btree structure? That said, you will need to be able to look at examples of the Btree structure. So here we go. This is a picture from the Btree section of those blog posts that we'll be going over. You'll need to be able to like look at this and understand exactly what's going on and how the query algorithms work. So not how the like insert delete algorithms work, but how the query algorithms work. There we go. And so the main difference between like the tree structures you've seen before and the Btree structure is that the Btree is optimized for being stored actually physically on a hard drive rather than in memory. So like these, AVL tree optimized to be stored in memory. The Lambda server has a lot of memory, 256 gigabytes. So you could store a pretty big AVL tree in there, But if we have terabytes or petabytes of information, no amount of memory is going to save you. You can't use an AVL tree. The Btree, since it can be stored on disk, arbitrary sizes of information, and it's very common for petabytes or even exabytes, the thing after petabytes, to be stored in Btrees. The key idea, the key thing that we need to know about hard drives in order to understand why the Btree is structured the way it is that it's really fast to find information stored close together, but slow to do what's called seek to new information. And so we have some pictures of hard drives down here that will help us illustrate that concept. So this is like a physical blowing up diagram of what the inside of an HDD hard drive disk looks like. And you have these circular disks that store the actual information, and this piece right here, the recording head that travels along these disks. The recording head will just move like inside and outside, changing the radius at which it looks. And the disks themselves are spinning at pretty fast speeds, so around like 2,000 RPM common speeds. And that's how the information itself is read. The structure of the information on the disk is organized into what are called sectors. So this information over here, this picture over here is what an older hard drive looks like. That's the easier one to understand. But a sector is one of these little sort of rectangular-ish things, and it contains typically about 8 to 16 kilobytes of information on it. Depends on how your hard drive is actually formatted and arranged. But a small amount of information. And every time you read from the hard drive, you have to read an entire sector at a time. You can't read one byte at a time. And so that property is why the Postgres has its pages structured the way they do, because one page is supposed to correspond essentially to one of these little sectors on the hard drive. Because of the way like circles work, things that are farther away from the center of the hard drive are going to have bigger rectangular sections. So modern hard drives have those sectors sort of blocked out with this sort of more complicated layout that's a little bit more efficient. But same basic idea. There's just chunks of space that you read them all at once, and you can't read small amounts. Can't read just individual bytes at a time. And again, because this hard disk right here is rotating, it's really fast to say if you have information right here in this sector right here, it's really easy to just leave your recording head right here in the same position and continue to read from the subsequent sectors that are arranged just next to it. You can get typically, like on a modern hard drive, hundreds of megabytes per second of throughput that way. But when you have to find information in a new location, whether that new location is on like the same radius level just far away, or if it's a different radius level and the recording head has to actually move, then it takes an incredibly long time, so on the order of like milliseconds, to actually move that recording head to the new location and get that new data. So the point of the Btree structure, is that these seeks, we call it a seek, when you're accessing a faraway information on the hard drive platter. These seeks are super expensive, like milliseconds, which is forever in computer to your CPU. And so we want to minimize the number of seeks that happen. And we basically don't care about like how much computation happens, because relative to these seeks, computation is free. We can do on the order of billions of mathematical operations in the same amount of time that it takes to do a single one of these seeks. So the Btree is going to trade off doing more, increase the amount of CPU operations in order to decrease the amount of disk I/O operations, and in particular the seeks. Super fast overview of HDDs. Any questions about how that works internally? Okay. Yeah, the main sort of competitor to HDDs is SSDs, solid state drives. Solid state drives have no moving parts, and so the seeks are significantly faster. They are still actually turn out to be, for various complicated reasons, more expensive than contiguous reads. And so even on an SSD, it makes sense to minimize the amount of seeks that you do. Okay, and so the key technique that the Btree uses is that instead of being a binary tree, it's going to be a high fan-out tree. So it's going to have many, many different branches instead of just 2 branches. In order to illustrate that, let's go and draw some example Btree structures over here to see what's going on and what our some basic definitions are. So let's say we have, we'll start drawing a binary tree. So we'll use numbers as our nodes. And the key thing about the binary search tree is that elements to the left are smaller than, so maybe we have a 10 over here, supposed to be a 10. Elements to the right are bigger, so a 30. And then we'll do 5 and 15 and 25 and 35 and 1 and 8 and so on. And so this is a relatively balanced tree. Again, the height of a tree is going to be super important. So the height distance from the root to the leaf nodes down here. And the height is going to be O of log of n, where n is the number of nodes. We can be, we'll get a little bit more particular about this formula though here in a second, adding some more variables to it. But this would be a valid AVL tree, red-black tree, binary search tree, any of the classic trees from data structures. In a binary search, or sorry, in a Btree, instead of having just one value per node, we have many values per node, typically drawn as a box here. And I'll put 4 values in this node. And let's go ahead and do, say, 10, 20, 30, 40. So different numbers than before, but the same idea. And then we're going to have a branch coming out to the left and right of each of these numbers. So lots of branches like this. If we have 4 different numbers in a node, we're going to have 5 different branches because we have, think of it as like 1 to the left of every number plus an extra 1 on the right. And then each one of these branches is going to have its own big set of nodes with 4 different numbers inside of it. And the main property that these numbers are going to satisfy is that, again, with that binary search property, but only on an individual node like this number here and not on all of these numbers together. So all the numbers, let's change the color so it's a little bit easier to read. All the numbers in this branch right here are going to be less than 10. So say do like 5 and 6. These containers here, these branches don't have to be full. They can be full, but they don't have to be. You can have some empty things. That's totally okay. And then over here, let's do 11. And let's see, don't have a lot of space in here, so I'll make this one pretty empty. And this one over here, I'll write small and get 2 numbers in there. Maybe over here we'll have, I'll try to fill it all up. 31, 32, 33, 34, And more numbers over here. I'll just say 41 like that. And so that's the basic idea of a Btree. And now we can do our binary search, in this case, not binary search, but our search of this tree following the same procedure that we did for a binary search tree. Only now, let's say we're searching for the number 35. What's the number closest to 35 in this tree? We start at the root, and then you go left to right on all of the nodes inside of this particular node here. So anytime you access a node in a search, you'll have to do a linear scan of all the numbers in the node. And if we say that there are B numbers, so the numbers inside of here are often called the fan out. So B equals the fan out. Then a linear scan is going to require O of B for accessing the node. The total number of nodes that we'll have to access is going to be the height of the tree. The height of the tree is now going to be smaller than the height of a binary search tree because we just have more nodes at each level, more numbers at each level, so the height can be much, much smaller. The height of the tree in particular is going to be O of log base B of n. And so as we increase the size of B here, we're going to decrease the height. B increases implies that the height will decrease. The total number of CPU operations that we have to do on our search right here on our query is, so every time we visit one of these numbers, we have to do some sort of comparison, like a less than or greater than or equality. And so it'll be O of B for each node. We'll have to visit log B of n nodes. So the CPU operations for a search is O of B log B of n. Any questions about where that number came from? Yeah, so the question is, where did this B right here come from? And the answer is that, so when we do a search, we're going to have to investigate one node at each level. So in this case, if we're searching for the number 35, we'll have to investigate this node up here until we hit between the 30 and 40. And we know that now when we descend, we'll have to investigate this node down here. And so because we investigate one node at each level, the total number of nodes that we investigate is the log base B of n. And because the runtime of investigating a single node is B, multiply those two things together and we get B log B of n for the actual query itself. Good question. Any other questions so far?
Sorry, I don't know if you have this before. So the right now we have the similar size of the lower level, right? We have the same.
Yeah. So there's many variations of Btrees, which we'll talk a little bit about here in a minute. But in general, the fan out is going to be the same for all of the nodes. The nodes themselves don't necessarily have to be complete, don't have to be totally full on their fan out. but there's going to be some, the total amount of numbers in there and the total amount of spots is always going to be O of B. And one of the tricks about the insert and delete operations that we're not going to talk about is that how do you maintain that property, and it's always the case that the number of numbers in one of these is going to be O of B.
So for the leaves, does it have to be in ascending order?
Yeah, good question. So the question is for the leaves, but in general for any node, do the numbers have to be in ascending order? And yes, every node individually, the numbers will be in ascending order. And then each child satisfies the property that the numbers in this child here will be between whatever these numbers are up here.
And so, but it can be, so in a child node, it can be like equal to the like corresponding parent node. So for example, on like the third leaf, 20 being the same as 20, doesn't have to be strictly bigger.
Yeah, so this is a good question. The question is, like here we have 20 and 20 being the same, and how do we handle sort of the strict equality? And that's, it basically doesn't matter how you handle that. You're going to get the same like asymptotic performance. The strict equalities could go to the left, they could go to the right. You could, in your node up here, just keep a counter that there's like 50 different 20s. So it'll just be convention on any particular implementation about how that's stored. Yeah, we're gonna see, so this is like the super most basic version of the Btree right here. The actual version used in Postgres is significantly more complicated. But this is like the key main idea to understand is just that, yeah, the numbers inside of a node arranged in order, and then somehow satisfying the binary search property on any particular branch right here. Good questions. Any other questions so far? Okay. So a question that you should be sort of asking yourself is like, how does this formula right here, how does this formula for the Btree compare to our previous formula for the AVL tree or any binary balanced search tree? And in particular for a balanced tree, that's equivalent to having B equal to 2. And so the question is, for a Btree where B is greater than 2, how are we going to have more or less CPU operations? So as B increases, so as we go farther and farther away from a binary search tree, how does the log B of n behave? And you can do the limits, work out the math, but it turns out that for every value of B greater than 2, this is going to increase. Anytime you increase B, this is going to be increased. So this is monotonically increasing in B. Anytime you increase B, this value over here increases. So anytime you increase the fan out, implies more CPU operations. And so if we had a small data set that was only being stored in memory, that would be bad because our bottleneck, our limiting factor, is the number of CPU operations. But when we have our data set stored on disk, again, the bottleneck is not the number of CPU operations. The bottleneck is this, this recording head right here and moving it to the new location. if we were using an AVL tree or any binary search tree, every time we hit a new node, we'd have to move this to a new location to get that new node's value. And there we go. So the total number of disk operations is just the total number of nodes that we access. Because again, when we access a particular sector on the hard drive, we can read it all at once. There's no difference in performance between reading the entire sector or reading just a single byte from that sector. So reading a 4 fan-out tree takes exactly the same amount of time as reading a 2 fan-out tree. So the total number of like hard drive accesses that we are going to do is the number of the actual number of nodes that we access. The number of nodes that we access is the height of the tree, so log base B of n. So increase B is more CPU operations, but the number of, I'll just write HDD for hard drive, but this is true for any type of hard drive. HDD seeks equals number of nodes. And this is the real bottleneck. And that's going to be O of log base B of n. And for here, for this bottleneck, increasing B implies that the log base B of n will go down. So number of hard drive accesses, HDD seeks, also goes down. And so the Btree increases our CPU operations. This is our number of CPU operations. The key idea is that it decreases the number of disk accesses. And for the large data set, that's the bottleneck for our application. And so that's why we care about the Btree. Any questions about that? Does that feel like it makes sense? See some head nods. Okay. So in practice, how do you determine the the optimal fan out? That if you set B too high, say setting B equal to n, then we only need one disk access, but there's only one node, but then our CPU is going to get too large. And so there's this sort of trade-off between making the fan out too large or too small. For Postgres, and this is true for most databases, but for Postgres, each node is 1 page, so 8 kilobytes. And so our fan out is going to be just for whatever the particular data type is, how many of those can we actually fit in 1 page? So it's not hard coded. For a fixed size type like an integer, then it's always going to be the same what the fan out is. But for a variable size type like a string, it'll change how many strings we can fit in a particular page, and so the fan out will change on every different node. In practice, for most Btrees and Postgres, B is going to be on the order of like 100 to 400-ish. And so this is a really, really high fan out. And if we took So like the total number of web pages on the internet, something on the order of like 10 to the 15. So you're probably never going to see a data table with this many entries inside of it. But if you did the fan out of this, then your height, so n equals that with b equals that, implies the height of the tree is only going to be about like 4 to 5. Vast majority of trees will have a height of just 2 to 3, and only exceptionally large data sets will have a height in the 4 to 5 range. And so this means every time you're doing a select statement, you're only going to have to read 4 to 5 pages to actually get to the right location to find the data. And so that's why, again, yeah, the login time, essentially like constant time. It's not one page you have to look at, it's 4 pages you have to look at. So it's like constant factor overhead. I think that's a good stopping point for us for today. Next time we'll talk a little bit about some of the variations of this Btree structure and start going into detail about the algorithms, about how Postgres is actually using this under the hood for all of the select statements, and how to make your queries faster using all of this knowledge here. Yeah, if people have questions, I'll stick around for them now, but otherwise I will see you, or I'll be available in office hours. And again, there's the quiz on Monday that you should all be prepared for.